Okay, we just have 2 lectures to go, doing today. So let's see, first of all, if we go to the website, I presume since you're all here, you're probably taking the final, or just extremely interested on the other. So of course you already are aware of your first grade efficiency exams, and so the final is on 12/12, Thursday 12/12. Now please note that it starts at 1:30, not 3 p.m. normal class time. It starts at 1:30. Okay, so if you happen to wander into here at 3 p.m., that's a big problem. So I'm just trying to point that out. Taking the final, it starts at 1:30 on Thursday 12/12. Now the final exam is going to be cumulative, with 50 questions, multiple choice, just like the other 3 exams. It's a cumulative exam, so you should use the study guides for the first 3 exams. And also review this additional material here, which just covers chapters 14, 15, and 16, which of course we covered after the 3rd exam. Okay, so let's go ahead and get started. We're actually not quite caught up at the moment where we need to be. All right, so the main topic today is solar system formation, but we're actually not finished talking about comets, so I'm going to pick it up at comets first of all. This is Comet Hale-Bopp, which is one of the more recent, really bright comets, and has this distinctive kind of double tail that we're seeing there with a light-colored, whitish-colored tail, and then also a bluish-colored tail. So we're going to talk a little bit about what's going on with those 2 different types of tails. Well, they only develop tails in the inner solar system. We'll talk a little about that because comets are basically very icy objects, and when they're far from the sun in the outer solar system past Jupiter, roughly, they are not going to display tails. They're going to be what we call cometary nuclei, which are very compact objects a few kilometers across. But the reason, of course, that they do get the tails that we associate with comets is because of the highly elliptical orbits that they travel on. I'll actually show you a plot of the orbit of comet ISON, which is the one that was supposed to have been the comet of the century a few days ago. There's an update on that, but we'll look at the orbit of that particular comet. Comets do not generate any internal energy at all. They're shined by reflected sunlight, which is basically what all moons and planets do when we look at them. As I mentioned, they're mainly ice, and when they're close enough to the sun, the ice converts directly to a gas. It does not go through the liquid phase. It converts directly to a gas, which is this process we call sublimation, and forms this thing called a coma, which is this cloud of gas that's hanging around the nucleus until it finally gets swept back by the pressure of the solar wind. So that cometary coma is maybe around 100,000 kilometers across, which is roughly comparable to the size of Jupiter or Saturn, something like that. So it's a big thing as it flies around the inner solar system, but it's not as threatening as actually having Jupiter or Saturn fly around, because this is an incredibly low density object we're talking about. A very thin cloud of gas that happens to have a radius similar to that of Jupiter or Saturn. And the tail always points away from the sun. But as I said, there's 2 types of tails. There's the curved dust tail and the straight ion tail. Okay, so we'll get that in a moment. So just picking up on another specific comet, Halley's Comet, same major axis is 18 astronomical units. That actually makes this a member of the class of what we call short period comets. It actually has a period of about 76 years. But notice the eccentricity figure up there, 0.967. So remember, the eccentricity figure, it kind of gives you a contrast between the perihelion, closest approach distance, and the aphelion, farthest approach. And when you get a number close to 1 like that, it's a very elongated orbit, much more elongated than I've actually plotted there. So we see extreme variations in the distance from the sun when we're talking about comets with high eccentricities. Okay, so again, if we talk about Halley's Comet with an eccentricity of 0.967, if we do the math for those 2 formulas there for the perihelion and aphelion distance, we get this tremendous variation. It comes within about a half an astronomical unit, a little closer to the sun than Venus, at perihelion, and at aphelion it's all the way out to 35 astronomical units, which puts it almost as far out as the orbit of Pluto, something like that. But its actual semi-major axis is about 18 astronomical units, about half that longest distance, because that's what happens when you get a very eccentric orbit. So of course, large variations in distance from the sun lead to changes in the amount of solar heating, and that of course is why we get the phenomenon of the tail when the comet is close to the sun. Okay, continuing with Halley's comet for now, if we take the semi-major axis to be 18 astronomical units, we get a period of 76 years. And that actually was one of the earliest predictions based on Kepler's laws and Newton's laws. And this is actually why the comet bears Halley's name, because he predicted it would return 76 years after its apparition at that time. And he was actually deceased by the time he came back, but everybody remembered his prediction anyway. And that's the reason that we call it Halley's comet. It's the first example of a comet that actually returned on a predicted timescale. Anyway, so this is a short period type of comet. We'll talk about what these two different classes mean. Okay, so we of course have Kepler's second law applying to any object orbiting the sun, or any object orbiting any planet even. We're going to have equal areas and equal times swept out, and that immediately implies that comets are going to move very quickly when they're near the sun, because that's the only way they're going to be able to sweep out equal areas and equal times when they have a very short radial distance from the sun. So the conclusion of that is comets don't spend very much time near the sun, because that's when they're moving faster. So they whip around the sun, and then they slowly decelerate, and they're moving very slowly out here. So they spend most of their time at very large distances from the sun. So these red dots that I have there sort of indicate equal time periods, and you can see that they're pretty close together out there, indicating that the comet is, not moving very quickly out there. Oh. Some comets look like ducks. That actually hasn't been ruled out, just saying. But the point of this is you can see that the duck moves a little faster close to the sun. That's what a comet would do, or any object, but it's most pronounced with a comet because they have such eccentric orbits, much more eccentric than any planet that we're talking about. Okay, so Halley's comet here, its last major apparition around 1985, so it won't be back again until around 2050 or something like that. You'll probably all have graduated by then. I'm here, but that's probably true. And so we see the characteristic, orbital shape there. We're going to have the appearance of the tail when it's near the sun. So Halley's comet right now is way, way out, approaching its farthest distance in 2024, and completely tailless at the moment. All right, so again, Halley actually was observed in 1708. It was observed in 1682, and using Kepler's laws, he made the prediction that it would reappear in 1758, and it did that. So it was dead, but still, as we say, it is forever known as Halley's comet, and that's the way it's always going to be. And in fact, if we look back to historical records, particularly Chinese astronomers and whatnot, very accurate historical records going back thousands of years, we can actually see recurrences of it back as far as 240 BC. Okay, so again, we're talking about a short period comet. Short period comets have semi-major axes that cause them to reside in this area we call the Kuiper belt, which is around the orbit of Neptune. Oh, what about this? Right. Okay. Actually, we're just beginning the semester, so I'm not sure. No. Not going to fall through that. Sorry. Can't take that risk at the moment, bringing down the whole system. But anyway, I would have been able to show you that there's a swarm of cometary bodies in this region we call the Kuiper belt, which is out around the orbit of Neptune. And again, these are short period comets. And then there's a whole other group of what we call long period comets that spend most of their time much, much farther away from the sun than the Kuiper belt. And remember, the Kuiper belt is out around 30 to 40 astronomical units. This Oort cloud that I'm talking about now is actually not a ring, it's a real cloud, like a spherical shell, like the shell of a soccer ball or something. But the radius of that shell is around 100,000 astronomical units. So we're talking more than 1,000 times farther out than this Kuiper belt. It's completely unrelated to the Kuiper belt, a whole other phenomenon in the solar system. And there's a couple of things to note about this. First of all, if they're that far out, of course they're going to have very long orbital times. Right? If you do the math, you get orbital times of 100,000 to upwards of 10 million years. So that's why we call these the long period comets. The periods are vastly different than what we just saw from the short period comets, which are like 100 years or so. These are on the order of at least 1,000 times longer than that, if not 100,000 times longer period. Okay, another difference between the Kuiper belt and the Oort cloud. The Kuiper belt is kind of a donut-shaped region. Okay? So if you look at all those Kuiper belt objects, it would sort of form a donut shape, kind of like the meteor, the asteroid belt or something like that, but it's farther out than the asteroid belt. And it's a donut-shaped region where we have the comets in the Kuiper belt orbiting pretty much in a single plane. Okay, it's a donut, so it's not really exactly the same plane, but it's kind of planar, if you will. Big difference with the Oort cloud is spherical. Completely different geometry than the Kuiper belt. All right, a couple other things about the Oort cloud. It's actually where most comets are. Right now as we speak, most comets are out there in the Oort cloud because it's this massive, gigantic structure with probably trillions of comets out there. But you don't look out there and see lots of tails and whatnot because it's so far from the sun. They're just icy bodies out there, no tails, nothing like that. They're icy bodies that are orbiting the sun at a tremendous distance. And occasionally, one of them is affected by a collision or interaction with another body, and that's why it drops into the inner solar system. That's actually a very unlikely thing to happen. Most of the Oort cloud comets spend their entire lives happily orbiting the Oort cloud for billions of years, probably. I mean, they actually would sort of go on forever. Nothing happens to them. It's only a tiny, tiny fraction that ever drop into the inner solar system. And it's because they had some kind of interaction that caused them to lose a lot of energy. So they don't have the energy to stay in orbit anymore, and they basically fall like a rock toward the sun, right in towards the sun. And if they really have very little energy, they'll get into the inner solar system, and then we'll see a tail form. Okay, the reason I have this nearest star here is because the scales that we're talking about for the Oort cloud are around halfway to the next star. So we're talking about the edge of the sun's gravitational dominion in the solar system. If one of these gets bumped, it might even drift away from the solar system completely. So that's the Oort cloud. It's where most comets are right now. There's far fewer of them in the Kuiper belt. So, okay, that actually makes sense. Let's go back, because I'm not sure all of you were ready for that. Why would a cometary body leave the Oort cloud? I just mentioned it's interacted with by something, and we can't rule out this possibility. Because we can't see that distance. But notice there's the tail only in the inner solar system, and the tail points away from the sun. Okay, here we get the tail right here. Tail points away from the sun, so the tail doesn't always lag behind the comet. It's not, it moves ahead of the comet when we go to larger distances. Okay, picture of the Oort cloud. Here's your radius, 500,000 or so, 100,000 astronomical units. Most of them are in this swarm out there, this three-dimensional swarm. And very few have those elliptical orbits that take the comet into the inner solar system, as I mentioned. Okay, so this is kind of an observational fact that this cloud is out there, and we also have the Kuiper belt with the short period comets. So when we get into discussion of the origin of the solar system, one of the things we're going to talk about is why would you get a situation like this? There's got to be a reason why you have this huge bunch of comets at a very large distance in the Oort cloud, and then another whole group in a very different kind of orbital configuration. You see so much closer, only around 50 astronomical units out from the sun versus 50,000. So that's that scale factor I was talking about. If we plotted the Oort cloud on this scale, it would be maybe a kilometer out from this room. So they're completely different scales.